Hey, it's me. It's your pocket tutor. And in today's lesson, we're gonna talk about the equilibrium of fluids. First of all, it is known that in nature we have three types of matter that are solid, liquid, and gas. A solid is anything that has its own shape and volume, like a brick, a potato, a tomato, anything that has its own shape and volume. A liquid, instead, is something that has its own volume but takes the shape of its container, like the water inside of a bottle. And the last one, a gas, doesn't have neither its own shape or volume, but it takes the shape and the volume of its own container, like the air inside of a balloon. A fluid, then, is either a gas or a liquid. So these two categories are defined altogether as fluids. In order to understand the equilibrium of fluids, we need to define pressure. So pressure is a scalar quantity and is defined as the ratio between the perpendicular force and the area over which the force is applied. We'll see later on how to describe in detail pressure, but just know that pressure is the thing that transforms the graphite inside of your pencil into diamonds. The unit of measurement of pressure is the Pascal and is defined as the ratio of 1 Newton over 1 square meter. In order to imagine pressure, just think of someone stepping on your feet. Now, if they have trainer shoes, it doesn't hurt that much. But if they have high heels, it hurts a lot. And that's because the area over which the pressure is distributed is much smaller in the case of high heels, and therefore the pressure is higher. And that's because if you have the same force applied, but the area is much smaller, it's somehow like if the force is concentrated on a smaller area. Now, in liquids, we have to see things differently, because as we said, liquids do not have their own shape, and thus we need to learn Pascal's law. That says that the pressure applied on any given surface of a liquid is transmitted with the same value on every other surface touching the liquid. So if we consider this picture here, and we're applying this force over this area A, we will have pressure equal to F over A. Now the same pressure that we are applying on this small surface is the same one that will be felt all over this surface touched by the liquid. Let's look at an example of this law, that is the hydraulic press. An hydraulic press is a device that is used to lift very heavy objects by using a very small force. It employs a fluid, usually an oil, contained in this volume. And the principle is in fact the one of Pascal's law, so that the pressure that we apply on a surface is transmitted all over the surfaces touched by the fluid. So let's say that we are applying a pressure here through this force Fa. So the first pressure, Pa, will be equal to Fa over Sa. The pressure applied on this small Sa area will be transmitted all over the place, and therefore also the pressure on Sb will be the same. This means that Pa will be equal to Pb, that is the pressure felt on Sb, and is equal to Fb over Sb. What this means is that by applying a force Fa on a small surface, we can apply a force Fb on a much larger surface. But how much? Let's imagine that we have that Sa is equal to 1 square meter, while Sb is equal, let's say, 10 square meters. And let's assume that we're applying a 1000 Newton force. So Fa is equal to 1000 newtons. This means that according to this relationship, we have that Fb will be equal to Fa over Sa times Sb. and this is equal to 1000 times 10 over 1, and is equal to 10,000 newtons. So by just applying 1000 newtons, we can generate a force of 10,000 newtons, and this is thanks to Pascal's law. But how can we know what's the pressure that a liquid is applying on a surface? Well, in order to do that, Stevin helps us. Stevin's law says that the pressure given by a liquid's weight is equal to this equation here. So the pressure is given by the Earth acceleration constant times the density of the liquid times the height of the liquid column, that is this value here. And this is independent on the surface that we are considering. Let's try to find the proof for this equation. Let's consider a fluid column like this one that has a base surface S and a height H. The volume of the liquid will be given by the surface times the height of the column itself. The mass of the liquid will be given by the volume times the density of the fluid itself, that is equal to the surface times the height times the density. As we've seen before, the pressure applied on the surface S will be given by the perpendicular force on the surface over the surface itself. In this case, therefore, will be given by the mass of the liquid's column times the Earth acceleration constant over the surface over which we have the fluid. So putting the value of the mass in this equation here, we will have that the pressure is given by the surface times the height of the column times the density of the fluid times the Earth acceleration constant over the surface. And in this ratio we can simplify the surface, and finally we have that the pressure is equal to the height times the density times g. And that's exactly what we've just seen. Now, the last concept to really get confident with fluids equilibrium is Archimedes' thrust. Archimedes' thrust is a force that a body feels when it's immersed in a fluid, and it is described by Archimedes' principle, which says that a body immersed in a fluid feels an upward force of intensity equal to the weight of the fluid that the body displaced. So anytime a body is inside a water, like ourselves, when we go to the sea and we go take a dive, we feel a force that is pushing us upwards. This is Archimedes' thrust. Let's consider this picture here. We have a body immersed in a fluid. This body has its own weight, but its weight is not the only force that the body is feeling. The body feels also an upward force, that is the Archimedes' thrust. And this force is given by this equation here, that is the Earth acceleration constant g times the density of the fluid in which the body is immersed times the volume of the body itself. You can see from this equation that these two parameters here, they give the mass of the fluid that has been displaced. The mass of the fluid times g, that is the Earth acceleration constant, is the weight of the fluid that is being displaced. Now this weight is almost like if we had a force pulling up the body from the fluid. And this is the reason why when we are into water, we feel like we weigh less. And this is all for today, where in summary we have seen what is the distinction between solids, liquids and gases, and which of them are called fluids, and just to recall, liquids and gases are defined as fluids. Then we have talked about pressure and how to compute the pressure in solids and the pressure in liquids, for which we introduced Pascal's law. After that, we've seen a simple example of Pascal's law, that is the hydraulic press, which is used to lift very heavy objects with small forces. After that, we talked about Stevin's law, which is the law that describes the pressure applied by the weight of a fluid. And as last, we talked about Archimedes' thrust, that is that force that makes object in a fluid weight less. And this is it for today. See you next lesson.